Today we discuss the integrals as the limit sums. Okay. Earlier we arrived at the integral f via the upper sums and lower sums, that is LPF and UPF and LPF, where P is a partition of over the interval AB. And in that case, the numbers capital M, small m, or small capital Mi and small mi, which appears in these sums, LP, UPF and LPF, okay, appears in these sums, are not necessarily the values of the function f, are not the values of the function of f, they are the values of f if f is continuous. Okay, if the f is continuous, that means UPF was summation capital Mi delta of xi, LPF equal to summation small mi delta of xi. But now we shall show that integration f dx equal to limit of a sequence of sums, in which capital Mi and small mi, are replaced by the values of f, that means f of x, the values of x. Okay, so for that case P with the partition of AB and T1, T2, Tn are the points such that this belongs to xi minus 1 to xi minus 1 less than equal to Ti less than xi, I equal to 1 to n, and then SPF equal to summation f of Ti delta of xi, summation I equal to 1 to n, f of Ti delta of xi means xi minus 1. So previous this sum is called the Riemann sum of f over AB relative to the partition P. Okay, previously the UPF was summation mi delta of xi and LPF was summation small mi delta of xi. Okay, so in that case this capital Mi and small mi is replaced by f of Ti. Okay, and this Ti is belongs to the an arbitrary point, and this Ti can be any point whatsoever of delta xi. Delta xi means this portion. Okay, we say that SPF converges to A as mu p tends to 0, that means norm of partition tends to 0, that is limit mu p tends to 0, SPF equal to A is a finite value. Okay, we say that SPF converges to A as mu p tends to 0, that is limit SPF equal to A, if for every epsilon greater than 0 there exists delta greater 0 such that mod of SPF minus A, this is less than epsilon. For every partition P of AB with norm mu p less than delta, and every choice of points Ti in delta of xi. Okay, so the definition of integrable function is a function f is said to be integrable on AB if limit mu p is tends to 0, SPF exists, and then limit mu p tends to 0, SPF equal to integration f of dx over a to b. Okay, So we can say that this definition is the second definition of the Riemann integrability. Okay, what is this? The Riemann sum SPF is converges to the, if we converges to the finite number, and then this is equal to the integration of f dx. Now we show that our previous definition was a function is Riemann integrable if integration f dx equal to upper integration f dx equal to lower integration f integration a to b f dx. This was the previous definition of Riemann integration. Now we can show that actually this definition implies the definition 2. So from definition 1 we arrived definition 2. So for that case, suppose this is whole, that means from by definition 1 the function is Riemann integral means integration a to b f dx equal to integration a to b upper integration f dx equal to lower integration a to b f dx. Let epsilon be any positive number. By Darbach's theorem, there existed delta. What was the Darbach's theorem? Delta greater 0 such that every partition P with norm P is less than delta, then UPF is less than upper integration a to b f dx plus epsilon. And since the function is integrable, that means upper integration equal to the total integration, so this is integration equal to integration a to b f dx plus epsilon. Again, by Darbach's theorem also, LPF is greater than lower integration a to b f dx minus epsilon. Okay, this is equal to integration a to b f dx minus epsilon. Okay, so these are the definition, or these are the theorem of Darbach's. Now if Ti is any point of the interval xi minus 1 to xi, we have LPF is less than equal to summation I equal to 1 to n f of Ti delta of xi less than equal to UPF. There is no confusion between this inequality, because this is the LPF. LPF means summation small mi delta of xi, and UPF means the summation capital Mi delta of xi. And also we know that small mi less than equal to f of Ti less than equal to capital Mi for all I. So this inequality automatically holds. So this is number 1, and this is number 2, and this is number 3. So from 1, 2 and 3 we can show that the summation f of Ti delta of xi, which is greater than integration a to b f dx minus epsilon less than integration a to b f dx plus epsilon. So this implies the summation I equal to 1 to n f of Ti delta of xi minus integration a to b f dx, this is modulus which is less than epsilon. This function thus the function is integrable, thus the function f is integrable according to the definition and 2. So here we arrive the definition 2 from the definition of 1. Similarly, from the definition 2, we can get the definition, first definition of integrability. Now we compute integration minus 1 to 1 f dx, where f of x equal to mod x by the definition of Riemann sum. Okay, we know that fx equal to minus x if x is less than equal to 0 and equal to x if x is greater than equal to 0. Okay, and let this is minus 1 to 1, this is interval, and we got a partition, this is x0, this is x1, this is x2, this is x3, and dot 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 dot, this is xn equal to 0, and this is equal to suppose y0, and this is y1 and y2. Actually here we divide by two portions, minus 1 to 0 and 0 to 1. So the points, the partitions point from minus 1 to 0 is xi, and from 0 to 1 the partitioning point are yi, and dot 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 yn equal to 1. And this interval, this sub intervals, this interval divided by into 2n equal sub intervals, 2n equal sub interval of length n, 1 by n. That means actually, that means this is minus 1 and this is 0 and this is 1. So this is equal to I by n, I is running from 1 to dot dot kore n, and this is xi are minus 1 plus I by n, and yi equal to I by n, and I equal to, in both cases I equal to 1 to dot 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 n. So this one, the first one is minus 1 plus 1 by n, and second one is minus 1 plus 2 by n, and this is I by n, and this is y1 equal to 1 by n, and this is 2 by n, and this is dot 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 dot, this is I by n, that means 1. Okay. And you can see here that this length of the subinterval is 1 by n, that means mu p is tends to 0, and delta of xi, the length of the each subintervals xi to xi minus 1 is also I by n, and this is equal to so this is 1 by n, delta of xi equal to 1 by n equal to delta of yi. Okay, in both cases, in both total length, so length of each subinterval is 1 by n. This is first thing, and also the summation delta of xi equal to 1 equal to summation delta of yi. Okay, I equal to 1 to n. Let Ti is belongs to delta of xi, and Ti dash is belongs to delta of yi. Also let Ti equal to xi and Ti dash equal to yi for I equal to 1 to n. Now SPF equal to summation I equal to 1 to n f of Ti delta of xi. That means this sum I equal to 1 means this from this to this portion. Again, rest sum is summation I equal to 1 to n f of Ti dash delta of yi. Okay, this is summation I equal to 1 to n f of ti means that means in that interval -1 to 0 interval, -1 to 0 interval, f of ti means is minus of ti into delta of xi plus summation I equal to 1 to n. F of ti dash means in that portion, that means 0 to 1 position, f of ti dash gives just ti dash into delta of yi, This is summation I equal to 1 to n minus ti means also minus of xi. So minus of xi delta of xi plus summation I equal to 1 to n minus ti dash means actually ti dash means yi, which is equal to into delta of yi. This is equal to summation I equal to 1 to n minus xi means minus of -1 plus I by n into delta of xi plus summation yi means I by n into delta of yi, and this is equal to summation I equal to 1 to n 1 minus I by n delta of xi means I by n plus summation I by n into I by delta of yi also I by n. So we get this is equal to summation delta of xi minus 1 by n square summation I equal to 1 to n plus I by n square summation 1 by n square into summation I. Summation delta of xi minus 1 by n square I equal to 1 to n I 1 by n square summation I equal to 1 to n, and limit mu p tends to 0 SPF, and mu p means actually 1 by n. So 1 by n tends to 0 means limit n tends to infinity, because mu p equal to 1 by n. This is tends to 0, so n tends to infinity. This is equal to SPF equal to 1. Since the limit exists, this limit is exist and this is equal to 1, so that means the integration minus 1 to 1 mod of x dx, this is equal to limit SPF equal to 1. So integration of modulus function over the interval minus 1 to 1 is 1. So this is the application of Riemann sum. There is another problem you can check. This is show that integration 1 to 2 f dx equal to 11 by 2, where fx equal to 3x plus 1. You can check this integration by previous method and using the Riemann sum. Now we discuss some Riemann integrable functions. So number 1, let a function if ab to r be continuous on AB, then f is integrable on AB. Okay, if that means every continuous function is Riemann integrable. We already discussed in your class this statement. Now move to the second one, is let a function f ab to r be monotone on ab, then f is integrable. Okay, so there is two cases. Is one, f is monotonic increasing, and second one is monotonic decreasing. Okay, so we prove for the function f is monotonic increasing. So let's prove. Suppose f is monotonic increasing, f is mi, monotonic increasing. Clearly f is bounded, f is bounded on ab, and fa is the lower bound and fb is upper bound. Okay, and also fb minus fa, which is greater than or equal to 0. Okay, now let p be the let us choose epsilon greater than 0, and let p be a partition of AB with is norm P, which is less than epsilon by AB minus FA plus 1. Okay. Let capital MR equal to supremum of fx, x belongs to xr minus 1 to xr, and small mr equal to infimum over the subintervals of the partitions. This is x belongs to xr minus 1 to xr, and this is fx. Okay, since the function f is monotone increasing function, so that means capital MR equal to f of xr, and small mr equal to f of xr minus 1. Okay, since the function is monotonic increasing function. So now UPF minus LPF equal to summation r equal to 1 to n mr minus small mr into delta of xi, which is the length of the subintervals. This is equal to summation mr means f of xr minus f of xr minus 1 into delta of xi r equal to 1 to n, and this is the length of the subintervals. We can replace by less than equal to r equal to 1 to n, norm p, delta of xi is replaced by norm p, and for which we here equal to is becomes less than equal to, and f of xr minus f of xr minus 1. So this is equal to norm p, because summation f of xr minus f of xr minus 1 r equal to 1 to n. Okay, and this is equal to norm p into this gives fb minus fa, and previously we considered this norm p is less than epsilon by f of b minus f of a plus 1. and into FB minus FA. So this is totally less than epsilon. So we obtain UPF minus LPF is less than epsilon. So that this implies the F is Riemann integrable. So we get every monotone function whichever is monotone increasing or monotone decreasing are Riemann integrable. Now we move to the next result. We know that every continuous function is Riemann integrable. The question is some discontinuous function is Riemann integrable? Is the discontinuous function is Riemann integrable? The answer is, suppose let a function f AB to R be bounded on AB and let f be continuous on AB except for a finite number of points in AB, then f is integrable on AB. Okay. That means if f possesses a finite number of discontinuity, then the function also remain integrable. This is very important and interesting theorem. Now we move to do the proof. Since f is bounded on AB, then there exists a positive real number k such that mod of fx less than equal to k. Let f be discontinuous on m points x1 xm such that x1 less than x2 less than dot dot less than xm. Okay. Now case 1, a less than x1 less than x2 less than dot dot less than xm, which is less than b. These are the finite number of discontinuity. Okay. So this is AB. Okay, we move to the next page. This is A and B. These points are, suppose, the point of discontinuity, and we enclose this discontinuous point by some non-overlapping intervals. Suppose this is x1 minus delta 1 by 2, x1 plus delta 1 by 2, and this one also enclosed by x2 minus delta 2 by 2, x2 plus delta 2 by 2, and dot dot this xm also replaced by enclosed by xm minus delta m by 2, xm plus delta m by 2. Okay. And also the length of each interval is delta 1, delta 2 and dot dot delta m. Each length of each non-overlapping intervals are delta 1 to delta m, and and a less than x1 minus delta 1 by 2 and b is greater than xm plus delta m by 2. Also, this sum of the lengths delta 1 plus delta 2 plus delta m, which is less than 4k, which is less than epsilon by 4k. Okay, capital MR equal to supremum of fx over x belongs to xr minus delta r by 2 xr plus delta r by 2. Small mr equal to infimum of fx x belongs to xr minus delta r by 2 xr plus delta r by 2. And since the function is bounded by k, so capital MR minus small mr, which is less than 2k. Okay, and also it is known that f is continuous between a to x1 minus delta 1 by 2, also continuous in the interval x1 plus delta 1 by 2 to x2. That means f is continuous on remaining m plus 1 subintervals, which are a to x1 minus delta 1 by 2, x1 plus delta 1 by 2 to x2 minus delta 2 by 2, etc. Okay, now choosing the partition over this interval is p1, this interval p2, and last one is which is xm plus delta m by 2 to be, for that the partition is pm. And since the function f is continuous over that interval, that means f is Riemann integrable over that interval, Riemann integrable also over that interval, and for that case u p k f minus l p k f, which is less than epsilon by 2 into m plus 1, k equal to 1 to dot dot m plus 1. Okay, so u p k f minus l p k f less than epsilon by 2 into m plus 1, where k equal to 1 to m plus 1. And since this pi is pi are disjoint partitions, so p equal to, suppose p equal to p1 union p2 dot dot union pm plus 1, then p is the partition of the interval ab, and now upf minus lpf, which equal to up1f minus lp1f plus up2f minus lp2f dot 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 plus upm f m plus 1f minus lp m plus 1f plus m1 minus small m1 into delta 1 plus m2 minus small m2 into delta 2 plus dot 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 mm minus small mm into delta m, because this is for the subinterval this, and this length, this product is for the non-overlapping interval, for this one. So, and this is less than epsilon by 2 into m plus 1, because each of this is less than epsilon by 2 into m plus 2 into epsilon by this, all this is less than epsilon by 2 into m plus 1, and they are totally into m plus 1, 1 2 3 dot 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 m plus 1th UPF minus LPF plus all m r minus small capital M r minus small m r, which is less than k, 2k. So, less than 2k into delta 1 plus dot 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 delta m. We also considered in the first portion this sum is less than epsilon by 4k. So, this is less than epsilon by 2, and this is less than epsilon by 4k, means this is also epsilon by 2, and this is equal to epsilon. So, the next page, UPF minus LPF, which is less than epsilon, and this implies f is Riemann integrable. Okay, this is the first case. And for the second case, in the second case, a equal to x1 and b equal to xm, that means the end points also the point of discontinuity. Then if a equal to x1, then the subinterval enclosing the points x1, the subinterval enclosing the x1 can be chosen a to a plus delta 1. Okay, that means we choose the subinterval which one is enclosing x1, which is a to a plus delta 1, and if xm equal to b or b equal to xm, then the subinterval enclosing xm is b minus delta m to b. Okay, in any cases we proceed the similar arguments, and we can prove that f is Riemann integrable. So, in both cases, that means the discontinuous point belongs to the interval or including the end point also. In both cases, the function is Riemann integrable. That means a function which has the finite number of discontinuity also be Riemann integrable. Okay. Not only that, there are also result if a function which is discontinuous in infinite number of at infinite number of points, such that the number of the limit points of that in discontinuous set of that discontinuity set S is finite. Okay, then also the function is Riemann integrable. Okay, that means f is discontinuous at infinite number of points, point set, suppose this is S. Okay, the set of discontinuity is infinite. Okay, and if the limit of the limit points of S is finite, then the function f also Riemann integrable. So, from that we have a remark, which one is a bounded function is continuous, means this is integrable. Number 2, continuous implies Riemann integrable. Number 2, continuous except finite number of points of discontinuity. is also integrable. And number 3, not only that, continuous with infinite number of points of discontinuity is integrable provided the set S of points of discontinuity has only finite number of limit points. Okay, so we get three remarks. These are the very important remarks. So we get lot of integrable functions. Every continuous function is Riemann integrable. Every monotonic function is Riemann integrable. Every continuous with finite number of discontinuity is also Riemann integrable. Every continuous with infinite number of discontinuity also Riemann integrable, provided the point of discontinuity is finite. Provided the set of points of discontinuity has only a finite number of limit points.